Hi everyone, this is Austin Hoggett here to give you another lecture from OpenStack's Intermediate Algebra. Today we're going to be focusing on how to solve quadratic equations once and for all. We're going to introduce today what's called the quadratic formula. And it's meant to be able to solve any equation that comes in the following form. We've talked previously about how to solve these types of equations using some different techniques. One of the first introductions to this topic is using factoring and the zero product rule. The factoring zero product rule allows us to use either special products or integers to factor the expression so that we can apply this zero product rule, setting each of those factors equal to 0 and using linear equations to finish the problem. But these have limitations. Some expressions can't be factored using our AC method techniques or any of these special product rule that we've seen before. So they have some limitations that make them a little limited. The second technique that we've discussed is the square root property. The square root property also has its limits. The square root property is only helpful in cases where we can actually isolate the square term, and it also sort of suggests that we really only have a square term. In other words, the square root property isn't helpful for cases like 2x squared plus x is equal to negative 72. So today we present the following solution, the quadratic formula. The quadratic formula is derived from another technique that's not mentioned here. The technique is referred to as completing the square. By completing the square for the generalized expression that we see here, we can find a solution no matter what the values of a, b, or c are, and regardless of how many terms are actually in the expression. The solution is always the same. We end up with a solution for the quadratic equation, negative b plus or minus the square root of b squared minus 4 times a times c, all divided by 2a. More recently, there's some other versions of this particular formula, but this is the most classic version. Let's take a look at how it's utilized to solve some more complicated looking expressions. Here's an example where I'm asked to solve by using the quadratic formula. But truthfully, we could also solve this using the AC method. By identifying factors that multiply together to give me a times c, which in this case is negative 10, we can also identify values m and n such that they add to give me positive 9. So if we let, for instance, m equal to 10 and n equal to negative 1, we ought to be able to split our middle expression, 9x, into two parts. By doing this, we can continue the factoring by looking at the first and second pair of terms. Factoring by grouping, we can identify 2x as the GCF amongst these first two pair of terms, leaving me with the binomial x plus 5, and a negative 1 as the common GCF for the second pair, also leaving me with the binomial x plus 5. These two factors can then be multiplied together to find the solution. The zero product rule tells me then that by setting each of these equal to 0, we can identify the two values that make our statement true. So we here get solutions of x equals negative 5 and x equals 1/2. So the other technique that we have is the quadratic method, which we'll introduce first by identifying the correct values for our coefficients. Our a term is the coefficient on the square value. Our middle coefficient, 9, is b. And lastly, c is negative 5. It's critical that the expression here is set equal to 0 before identifying these a, b, and c values. Again, our formula is given as negative b plus or minus the square root of b squared minus 4 times a times c, all divided by 2a. Substituting our numbers into the equation here is the easy bit. The tricky part is trying to simplify this mess of a radical, and of course, that's the challenge. Going through and simplifying the radical, we'll start by squaring 9 to get 81. The product of these three terms, -4, 2, and -5, should give me a positive 40. Again, we have division by 2 times 2, which is 4. Continuing the simplification here, we get -9 plus or minus the square root of 140 plus, or excuse me, 81 plus 40, which is 121. All divided by 4 still, which can be reduced to -9 plus or minus 11, all divided by 4. Separating our numerators into two pieces, we might say that this is -9 plus 11 over 4 and -9 minus 11 over 4. Each of these expressions will give us our two results that we already know to expect, 1/2 and -5. This is an example where either method seems appropriate, and there's not really a shortcut in either case. But not all quadratic formulas are capable of utilizing all two or three techniques. Let's look at another example. In this case, we can still solve using the AC method, but instead let's start by setting the equation equal to 0 and using the quadratic formula. I want to start here moving my variable term, or excuse me, my constant term to the left-hand side. Again, this is necessary because we need to appropriately identify our A, B, and C values for the formula. Given the setup here now, I can tell that my A value is 1, B is -6, and C is +5. Again, the formula for the quadratic formula function is -b plus or minus the square root of b squared minus 4ac all over 2a. If you have trouble memorizing this particular formula, I completely understand. It's helpful to get this tattooed to the back of your eyelids. Continuing, we make our substitutions into the equation, and it yields the following. 6 plus or minus the square root of -6 squared minus 4 times 1 times 5, all divided by 2 times 1. So continuing the simplification here, I get +6, notice the sign change here, plus or minus the square root of 36 minus 20, all divided by 2. This can be reduced slightly to give me a square root of 16. And then, just as before, reducing the square root to its simplest form, we get two statements. 6 plus 4 divided by 2, and 6 minus 4 divided by 2. This yields our two solutions of 5 and 1. This is a quadratic, in other words, a second degree equation, so we should expect there to be two solutions. Again, we could use the AC method for this technique, for this problem as well, but we're not always guaranteed to be the case, and it can be difficult to pick which examples will or won't be capable of being factored beforehand. Now let's look at another example. Given, in this case, our expression 2x squared plus 10x plus 11, we might be tempted to try the AC method. However, considering the AC method, we would have to find factors of 22 that add up to +10. And there's not any that answer those questions that would be required of us to continue using the AC method. So the limitation here kind of begs that we use another technique. The quadratic formula, however, is always handy. And so by identifying my A, B, and C values here, we can start to make our computation. Again, we get -b plus or minus the square root of b squared minus 4ac, all divided by 2a. By substitution into the expression here, we can simplify a bit. Under our radical, we end up with the square root of 100 minus 88, all divided by 4. My square root is typically the most important part of this process. It tells me something specific about the types of expressions I'm going to get for my solutions. Notice in this case, when we do our multiplication and simplify that root, we end up with the square root of 12. While this isn't an integer value, it will at least reduce down to some expression we can handle. So continuing the process here, we'll split our square root of 12 into square root of 4 times the square root of 3, reducing to plus or minus 2 square root of 3. We've seen this before where we have common factors that can be reduced if we were to split our expression into two parts. For instance, negative 10 over 4 could be reduced to negative 5 halves, and 2/4 times the square root of 3 could be reduced to 1/2 times the square root of 3. Again, we could place this back together in a more succinct format, but both of these versions are correct. Let's take a look at another example here. As usual, we start off with some expression that should be rearranged to the standard form. By moving our constants to the same side, we end up with the following trinomial, set equal to 0. This gives me my a value of 4, my b value of negative 20, and c value of 25. These are rather large numbers, but as we kind of slip them into the quadratic equation, we'll find that the computations aren't too difficult. Phew. Now, as we go through and simplify again, the task at hand is really to focus on this square root. Negative 20 squared gives me 400. Negative 4 times 4 is 16. And negative 16 times 25 gives me also 400. In other words, my radical is going to go to 0. The square root of 0, of course, is just 0. And so all I'm left with is, well, 20 over 8, which can reduce to 5 halves. In all the other examples, we've talked about these being second order equations, second degree equations that are going to have two solutions. So why is it that we only got one in this case? The truth is, again, the radical expression is what's critical. In our quadratic equation, the expression underneath the radical is given as b squared minus 4ac. This is also referred to as what's called the discriminant. What does the discriminant tell me? The type of solution I should expect. If, for instance, the discriminant is negative, it suggests that the type of solution I'm going to get is two complex numbers. If my discriminant happens to be positive, meaning the square root is positive, we should get two real numbers for our solutions. It may be irrational, involving square roots still, but they'll at least be real numbers. And lastly, we have the current circumstance, which is when our square root of the expression is 0. In other words, the discriminant goes to 0. This suggests that we have only one real solution. More about this can be learned from actually graphing the equations themselves. but this is outside the scope of our discussion for today. Here's one last example. What's making this problem difficult is probably the anxiety around all the fractions. First, let's start by setting this equal to 0. Again, we need to identify our a, b, and c terms so that we can plug them into our formula. The computations in this case involved may seem a little bit intimidating. As we go through here, maintain some strength in at least plugging in all the values first before you start to panic. So let's reduce where we can. The first term, negative 2/3, is going to stay the same. Underneath our radical, though, something like 2/3 squared means to multiply 2/3 times itself. Well, 2/3 times 2/3 should give me 4/9. My second expression, negative 4 times 1/2, can be reduced to just 2. Negative 2 times 1/3 should give me a positive 2/3. In the denominator, half of 2 is just 1, so division by 1 essentially makes the denominator go away. So a lot of the difficulty of this computation, again, can be reduced by the fact that our denominator is quite easy to work with. But underneath the radical, we've actually got to be able to add together these two expressions. In this case, we can create an equivalent expression for 2/3 that has a denominator of 9, which would allow us to add them together. So 2/3 times 3/3 gives me to 6/9. Again, the purpose of which is so that we can actually add together our two expressions underneath the radical. So 4/9 plus 6/9 should give me 10/9. This can be reduced then using the quotient rule. We end up with negative 2/3 plus or minus the square root of 10 over the square root of 9. And lastly, we reduce and get negative 2/3 plus or minus the square root of 10 all over 3. Alternatively, we can put this back together as negative 2 plus or minus the square root of 10 all over 3. From the outset, we ended up recognizing, for instance, hopefully at this point, we would have at least a real solution, and two of them at that, because we have a positive radical. While the formula here can be difficult to memorize, the utility of it is like trying to make sure you use a jackhammer to tighten a screw in the door. It may be overkill, but it'll definitely get the job done.